Hello everyone. So in the last session, we looked at footprints. We looked at what are footprints, how do we assign them, and what to do if some footprints are missing. Now in this session, we are going to actually make the physical layout. We are going to place the components, we are going to fix their orientation, and we are going to connect these components. We'll also look at something called as DRC, Design Rule Check. We'll understand VIAs, how to use them, as well as we're going to understand field zones. So first things first, we need to arrange each one of these components. Right now they're kind of sticking together by default when we updated our PCB. And now we need to actually decide where each of these components will sit on our board. And while arranging these components, a few things to keep in mind is we want our connectors, for example, this power supply, this motor output pins, these pin headers on the edge of the board. Let me show you. So this is our actual board. So as you can see in this board also, they have put these connectors, this motor connector, this power connector as well as the pin headers on the edge of the board because it is very easier to put the wires on the edge of the board rather than the middle. Now imagine if these connectors, if these power supply pins, if they were on the middle, it would be very difficult for us to place our wires there. So let's just get back to the PCB editor and try to arrange it in a way that the pin headers are on the outer side of our board. We also want to separate different parts of the circuit and group them together. What I mean is, see, here we have our power supply. So this section of our circuit, it gives the power to our motor driver. These are the input pins through which we will control the motors. These are the signal pins. So this forms a different section, and this is where we are actually connecting these motors. So roughly there are three different sections. It is a very simple circuit. So we have three different sections, but your projects could be much more complicated than this. There could be more than 10 different sections. In that case, what we want to do is arrange each of the sections separately. Okay, so let's just get back to the PCB editor and try to select these components and arrange them in an optimized manner. So first thing what I want to do is select this power supply. Okay, now a clean way of selecting multiple components is just going back to the schematic editor and selecting them here. So for example, if I select all this power supply unit which we have here, it will be reflected in the PCB editor as well. See, these components are being highlighted. That means they are being selected. Now, if I press the M key, I can individually separate this power supply group from the other components. See, so I'll just place them here. Okay. I'm noticing one thing that this capacitor that I have placed is an axial one. See here the footprint is assigned is an axial and it's lying horizontal. But it's since it is taking too much space, let's just change it to a vertical one like this one. So this is a radial one. Okay, so let's just quickly change it. And how do we change it? We can simply right click here and click on change footprint, and we'll click here new footprint library ID. We'll click here and we'll change it to a radial one. So radial 10 mm. This looks fine. Okay, so let's just use this one for now. I'll double click and click on change and close. So we have changed this capacitor because it was taking too much space. So now we have our this power supply circuit, this one. So this is the part of our power supply circuit. Now let's just try to erase these components. So this is our terminal block. Let's just bring this here for now. I'll arrange it here, then I'll bring them here. So I'll click it and I'll press M to move it around like this. I'll just place it here. This is the jumper which is connecting the power supply to our voltage regulator. I'll place it somewhere here. Next we have this voltage regulator which is converting 12 volts to 5 volts. So I'll place it somewhere here. And next we have is the C2 capacitor. I'll place it somewhere near. This is fine. At C1, I'll place C1 here. I can rotate it so that the ground is on the other side. Notice that this C2 is slightly bigger than C1, but it's okay. This is just for a learning project. So that will be our placement for this power supply part. Now let's just try to arrange these diodes. This let me show you these diodes and these motor output pins. Okay, so the neat way of doing is selecting them is just selecting them on the schematic editor, going back to the PCB editor. As you can see, these things are selected. I'll just click on and we can move them around a bit far away here. So I'll just place them here for now. Now we want to connect these diodes to each other. Okay, as you can see in the figure in the schematic, this D1 is connected to D5, D2 is connected to D6, and so on. So let's just first separate these four diodes D1 to D4. If you select here, then it will be reflected here. So I'll just move them here, and similarly now I'll select D5 to D8. Sorry, I'll click M and I'll just drag them down. Now I can easily connect these two diodes. We'll come back to it how we are going to connect these two diodes. But for now, let's just first find some appropriate place for all of our components. Now I'm going to move this output motor pin somewhere here. Press R to rotate it. This seems okay. I'll rotate this as well. Press M and place it somewhere here. So I think we have roughly placed these 8 diodes and our motor output pins. Now let's just place this L298 IC and start connecting each of these components. So I'll just bring this somewhere here. This looks fine. You may notice one thing that our components are kind of scattered away. We have our power supply here, we have our motor driver IC here, the diodes here, the output pins of the motors here. Ideally, what we do is we create a boundary first. Okay, we'll create some sort of a boundary first, and inside that we'll place the components. But for this session, I'm keeping it very simple and we are going to place the boundary a bit later. So let's just try to uh, connect these diodes first. I'll grab these diodes a little bit upside this one and this one so that we can connect something like this. I'll bring this diode D2 in between here and D6 here, D3 a little bit upside, D7 upside, and D8. Good. This looks fine. Now let's just try to bring the other components closer to this setup that we have here. Uh, I'll bring this whole power supply thing a bit closer. Maybe move this capacitor a bit closer, this one a bit closer so that it can fit into that space. I'll move this here. Okay, maybe let's move the motors a bit to the side. Okay, I'll bring this here. This looks fine for now. I'll bring this in header somewhere, let's say here or here. Fine. This pin somewhere here. Yeah, and these are the two test points through which we can measure the amount of current that is flowing into the motor. For now, I'll just keep them here. So this is the rough placement of our components. This is not ideal at all. There is a lot of space in between, but just to understand how things work, I think this is good enough. So now what we want to do is actually connect these components to each other, and we do that by a thing called routing. On this right tab, you can see this option called route single track. Okay, and if I just click on it, a pen will appear. Okay, we just zoom in on this diode. Let's say I want to connect these two diodes now. So if I click here, you'll see that KiCad automatically highlights the points or the components that you want to connect to this point. Okay, so for example, this D1 diode, you can see this red line here. This is called a trace. Okay, trace. Think of these traces like wires that will conduct the current or some signals. Okay, so you can clearly see that this point is highlighted, this point is highlighted. So it means that we need to connect our wire to this point and as well as this point. Okay, and how are we getting this, how is KiCad getting this information that this diode needs to be connected here? It is getting this information from this schematic right here. See, this diode D1 is connected to diode D5. Okay, let's just get back to our schematic. Uh, Before we proceed further, there is one important concept that you need to know before we continue with our routing. That is the trace width. Okay, so if I click on this trace, you will see below this, its width is 0.2 uh, mm. But the thing is, we are using motors, right? We are using motors and they consume a lot of current. Okay, they consume a lot of current. So, what will happen if we don't use this trace of some appropriate width? Okay, then this might burn out. Okay, this width might not be sufficient to carry a large amount of current. Okay, let me just show you a picture so that it will be more clear. So you can see in this picture, this is our trace that we have just drawn. This the red line that you see on the PCB editor, and this is the width of the trace. Okay, but for a large current, we want our width to be a bit larger. Okay, we want this width to be a bit larger. Now the question is, how do we decide what width do we need? Okay, how do we decide what width do we need? So typically, if the current is large, we need a larger width. But how do we decide that? So for that, in KiCad we have a tool. Okay, so if you go to the KiCad default window, you will see a calculator tool. Okay, and if you click on it and come down to this track width. Okay, if you come down to this track width, you'll see something here. You'll see on the right hand side something called as track width. Okay, so if I put my current, okay, let's say if I put 1 ampere. Okay, 1 ampere is our current. Then you can see the track width. It is automatically calculated by using the formula of IPC 221. It is calculated this width to be 0.3 mm. That means it is safe to use 0.3 mm for 1 ampere of current. Okay, but if we put 2 ampere here, you can see the width increase to 0.78 millimeters. Now, how do we know what current that we are going to use? For that, we need to refer to the datasheet of the L219 IC. So let's just open the datasheet of the IC. So I have opened the datasheet of this L219 IC, and if you scroll down, you will see that in DC operation, the maximum current it is 2 ampere. Okay, so that's where we are getting this value of 2 amperes. Now if I put 2 amperes here, you can see the track width that is being suggested is 0.7 millimeters. Okay, so let's just get back to our PCB editor and change this, change this track width to be a bit larger. Okay, currently is 0.2 mm. And how do we do that? Okay, so we can do that by going to this left tab and click on edit predefined sizes. For me, it is showing 1 and 2 mm, but for you, probably it would show. So you can click on edit predefined sizes, and you can click on this plus symbol and add, let's say, 1, and hit enter. Okay, and click on OK. Now, you can select this 1 mm trace. And now, if I delete this wire by clicking on it and pressing on the delete button on my keyboard, and select this track 1 mm and click on route, you'll see the trace, the track is much more wider now, right? So I'll click here, I'll get these two connected. Similarly, I'll connect these diodes as well, these two, and this here as well. Now let's just connect these 12 volts as well. Let's click on it, this grounds. Now it's a very good practice not to just randomly start routing from one component to another component. The best practice is to divide your entire circuit into modules. So for example, here you can see that this is this is a power supply module. So what you want to do first is do it systematically. Let's just say you first finish this power supply, then you went to this signals, then you completed this diodes and motor drivers. But in our case, it's a very simple circuit, so we can jump around one module to another. Okay, so I'll just quickly go back to our circuit. Now I'll actually try to finish up routing this power supply module. Okay, so I'll click on this single track. Now start with our 12 volt supply. So this is the 12 volt supply. Either probably will supply battery here, and this is through a jumper which is going to the voltage regulator. This voltage regulator is connected to this capacitor, and this capacitor as well, and this 5 volts is connected to this terminal as well. For now, let's just not worry about this ground part. I will come back to it. We'll introduce a topic called draw field zones. There I will cover these ground nodes. So for now, let's just skip these grounds. Now this 12 volt is also connected to these diodes as well as the IC. So I'll just connect this IC somewhere like this. This is fine for. And I think we've taken care of all the 12 volts. Now we let's just connect the motors as well. So this motor is connected to this terminal. The other terminal is connected to D8 and D4 are connected here. This is connected to. Okay, now you can see that I'm trying to connect this outer terminal of the motor, but I'm not been able to go through. This is because we have these 12 volt lines already placed. So what we can do is actually change our layer. Okay, so I'll press escape. You can see here on the layer tab that this is a front layer that we're currently working on. By default, it will have only two layers, the front layer and the back layer. We'll add more complicated circuits where we'll need more than two layers, but for now, we'll just stick to two layers. And if I click on this B.cu, which means back copper layer, now we'll be able to route it in the back layer as well. So you will see that I can now actually cross this red line, right? Before I was not able to cross this red line, but now I'm able to cross this red line. Okay, So let's just connect this as well. I'll go somewhere like this, this, and I'll go something like this. Fine, this is not that ideal, but let's just keep it for now. We can optimize it later. I'll go back to the front layer and I'll just try to connect this here and this here. So I need to connect this point here, but there is no direct way. So I'll just go back to the back layer and connect it something like this. I think we've covered almost all the power tracks. Oh, we have one 5 volts here. So let's just connect it to the 5 volts by the voltage regulator. There we go. I'm intentionally leaving this ground for now. I'll just come back to it in a minute. We also have this net here. I forgot to mention one thing that you will see this the small lines that will actually show you which points are connected to which point, right? So if you can just zoom in and you see that this net U1 sense A is actually there is a line here and it's been connected to this R1. Okay? This is just for visualization. Okay, so I think we have covered almost all the power tracks. This one was left, so I connected it. Now let's just try to connect our signal tracks. So let's just see. We have E and A here. Now you'll notice that for signals we don't need this 1 mm track width. Okay, so I'll just quickly change it. So by default, if you so by default, if you click on use net class width, it will go back to this thinner width of 0.2 mm, which is sufficient for our signals. So I'll use that. So I'm in the back layer now. It's fine. So I'll connect this E and A somewhere here. This is fine. Just connect E and B as well. So E and B. Okay. Maybe I can somewhere like this. It's fine. While routing, we want to avoid these right angles, this right angles. I'll explain it in the next sessions. We'll cover it in detail, but for now, let's just keep it as a rule of thumb that we want to avoid these right angles. So I'll click on this track, and I'll press the key D, and I'll just slightly adjust it. For now, it looks good enough. Now, let's just try to connect our input one. I'll just move on to the front layer. Just click on it and let's see. You can see that there is no very direct way through which I can connect this. There is some way, but it looks very complicated. Right? This route looks very complicated. So what we can do is we can route the signal from here, then we can actually go to the back layer and continue from there. How we're going to do that is by using something called as vias. Okay, VIAS, vias. So let me just explain.
To understand vias, first we need to actually look at the structure of a two-layer board. Now you can see that actually there are multiple layers, but it is called a two-layer board because two-layer means there are two layers of copper. Okay, so this is the top layer where copper is present, and in this bottom layer as well, copper is present. So let me just briefly give you a rough idea about all these layers. So at the core we have this solid layer. This is an insulating layer made up of a material called FR4. FR4 stands for flame retardant 4. This layer is made up of fiberglass and epoxy. So it will act as an insulating layer between these copper layers. Okay. So next we have is this. These are the copper layers. Okay. These are the copper layers. Cu. Cu stands for copper. These copper layers are the layers where the action happens, where the current and signals will flow. And next we have this top solder mask and this bottom solder mask. So these are actually two protective layers used to prevent any short circuit during the soldering process. So let's just go a bit further and understand what exactly happens when we manufacture these PCB boards. Okay, so you will have your copper layers here. Okay, so this whole layer, this whole plane is filled with copper. Okay, this whole layer is filled with copper, and now when you actually draw your traces, okay, it will be something like this. Okay, let's say this is a trace. Okay, pardon me for my very bad drawing skill. Let's say this is some IC. Okay, and this is some trace. Okay, and let's say this is also some trace connecting some different component. This is some different IC. Now what happens when manufacturing is the copper is actually removed from all the other places. Okay, it will be removed from all these places. It will be only present here. Okay, it will only be present here, and thus you will have your connection between these two ICs. Okay, so it's not the other way around. It's not like that once you draw your trace, then the copper will be applied. Actually, what happens is where you draw your trace, where you draw your this routing tracks, at those places the copper won't be removed, but at all the other places the copper will be removed. Thus, it will establish a connection between these two components. I hope I'm clear with this. So I've quickly drawn this again. So let's just say we routed one track from here to, let's say, something like this here. Okay, we routed one track in this PCB board. We routed one track from here to here, and here is some component. Okay, now when we actually print this and give it to the manufacturer, what he will do is he will keep the copper on this trace. Okay, he will keep this copper on this trace, and the manufacturer will remove all the other copper. Okay, so this whole plane, at first this whole plane is copper, and then he will just remove the copper. The manufacturer will remove the copper from all the other places except for the traces and some fill zones. We'll come into this fill zones in a minute, but I think this point is clear how traces are actually manufactured. Now, coming back to our this structure, the cell screen is actually where we put our labels. Okay, so you will have your board something like this. Let's say you have some component placed here. Let's say this is a resistor, and to label it, we'll put some letter here. Let's say R1. So this R1, it will be written on the PCB, right? So this is where this R1 is written in this cell screen. So cell screen is nothing but it's just a labeling layer where we put our text, anything that we need on the on our PCB. So now let's just quickly understand what are vias. Okay, so vias are nothing but holes that connect two or more copper layers. Okay, so for example, this is a through hole via. It is going through the entire board. Okay, it is going through the entire board. There are also other kinds of vias. For example, this blind vias, which will connect an internal layer to an outer layer. Some buried vias which will connect only to internal layers. So this via will connect this layer and this layer. We will explore this buried blind and other vias on later sessions. Since now we only have a two-layer board, we'll mainly work with this through-hole vias. Okay, so what it will do is, let's say we have some component here, right? We have some component, some IC here. So it will help us route our tracks or route the signals from one layer, from this layer to, let's say, to this layer. Just to give you an analogy to make this through hole via concept very solid. Imagine you have a paper, okay? Let's say this is a paper, okay? And you have some thread, okay, some string or some thread. So let's say this thread is your trace. Okay, in our case, let's just say this is our trace. Okay, the copper trace. Okay, or the wire, anything. Now we want to move this trace to this other side of the paper. Okay, so what we do is we put a tiny hole, or we punch a tiny hole into this paper. We put our thread, or in our case the trace, and we can bring this thread through the paper to the other side of the page or the paper. So now I think this through hole via concept is clear. It's just a hole that is connecting two layers of our PCB board. Okay, so let's just get back to this PCB editor and see how we can use these vias in our design. Now we are back in the PCB editor, and I think we've covered all the power signals, the 12 volts and the 5 volts one. The only thing that is left is now these grounds and these inputs. Okay, ground we are going to cover a bit later after we have covered the signals. I'll introduce something called as fill zones, where we'll see where we can deal with these ground nodes. But for now, let's just try to connect these signals using the concept that we have just learned, which is vias. Okay, so I'm currently in the back layer. Okay, so we need to connect this input one in this pin header. Okay, so what I'll do is go to the front layer and click on this input, and we're going to use a via. Okay, I'll click on right click, then you can see this option, place through via. I'll click on place through via, and you can see this tiny circle that is appearing. Okay, now if I click again, you see our trace has changed the color to blue, which means that we're currently in the back layer. Okay, so let's just bring it somewhere near here, and we're going to place another via just to bring it back to the front layer, because there is a blue because there is already one trace which is kind of blocking our way. So we're going to use another via here. I'll click on right click, and we'll just go through here, in between here, and we're going to connect this to input one. Okay, well, we're going to do a similar thing for this input to signal. So right click, place through via, go downwards, place another via here, route it between this 5 volt and the ground pin of the capacitor, and this input 2. So I'll just quickly fix this right angle. I don't like the right angles. Okay, this looks fine. Now let's just try to connect this input 3 and input 4 as well. For this input 3, I can go to the back layer, and I'll maybe route it something like this. This looks fine. And for I think input 4, we can maybe go to the front layer and route somewhere something like this. Let me quickly fix this right angles. I'll press the D key to slightly bring it forward. This one as well. Yeah. So our signals are done almost. Our signals are almost routed. The only thing we have left is this test points which we included for measuring the current. So let's just move this R1 and TP1 somewhere, maybe let's say here. This looks fine. I'll also move this TP1 closer to, let's say here. So this will measure the current in the motor 1, and I'll bring this one here. Uh, Here is fine. R2, try to bring it maybe here, and it's fine. Yeah, R2 will, okay. Now let's just quickly connect these two resistors. Select this. Okay, I can maybe rotate this register here and here. I'll move this TP2 and R2 somewhere here because the pin is actually here. I thought it was here, but that's okay. We can just quickly move it, rotate it, place it somewhere here, and quickly connect it, place to via and connect it, remove the right angle. Now I'll place to via, connect it, quickly fix this one as well. So I think we've connected all the signal and the power pins except for the grounds, of course. Please note that this physical design that we're making is not very optimized. As you can clearly see, there are some spaces left everywhere. So this is not a optimized design. There are also some undisciplined routing here. But in this session, I just wanted to give you the idea of routing and some very brief concepts. So as we move on with more sessions, we'll actually try to optimize our circuits, optimize our design in terms of space. I have intentionally make this circuit a bit bigger so that it's clear to see everything. But we are not going to manufacture this board at all because this is not optimized at all. Okay, so let's just quickly move on to connecting our grounds. Okay, before that I see that we haven't connected these 5 volts, so let's just quickly connect the 5 volts here as well as here. Okay, let me fix this. Yeah, so now the only thing that electrically left is to connect our grounds. Okay, so for that I'm going to introduce you to a new concept that is called draw filled zones. Okay, it's available here. You can see draw filled zones. So what it does is it covers an area entirely with copper. Okay, it will flood an area entirely with copper, and we can assign which component or which net we are going to connect it to. Okay, I'll just show you how it's done. So I just clicked on this draw fill zones, and I'll maybe click somewhere here, and you will see this dialog will pop up where you see no net will result in an isolated copper island, which means we haven't assigned anything to that copper fill. So let's just assign the ground. Okay, and currently I think we're in the back layer, which is fine. So let's click on OK. So you can see now we can draw a rectangle which is covering the entire board. Okay, so what it will do is it will create a rectangular copper zone, and it will connect everything that needs to be connected to ground. Okay, there are also some other reasons why we need to include copper field areas of ground. For example, it reduces noise, which we are going to cover later. I just want to just introduce this zone filling for now, and we're going to cover it in detail in the next sessions. Okay, so now what we're going to do is we're going to press the B key. Okay, just press the B key and it will fill the zones. Okay, so now you can see, now let's just see this ground that we haven't connected yet is being automatically connected to this huge copper, this huge copper filled area, right? So wherever there was ground, see, this ground is automatically connected, this ground is automatically connected. And why is it automatically getting connected to ground? Because we have assigned this whole copper area to be ground. Similarly, we can add another such ground layer in the top layer as well. So let's just quickly do that. I'll draw another, I'll assign it to ground, click on OK, and draw something like this, and I'll hit the B key on my keyboard, and we have two ground zones both in the front layer as well as the back layer. So our board is almost ready, but before that I just want to include another small concept that is very important, which is called stitching vias. Okay, So what stitching vias does is connects the two ground planes or two ground zones. Okay, so you see we have this copper zone at the top layer, right? This top layer, and we have this copper zone at the bottom layer, but they are actually not connected, right? So let's say we have some power hungry or current hungry component at some place, let's say this area, and we want a really good return path for this current. Then what we're going to do is actually put some vias. Okay, we will put some vias that will connect these two ground zones. Okay, remember that this is also a ground zone, this is also a ground zone, this is also a ground zone. So stitching vias, what it does, it connects these two ground zones. Okay, ground zones in different layers. Okay, so we're going to place some stitching vias near, I think, the capacitors and as well as the diodes. Okay, so let's just quickly place some stitching vias near this capacitor here, the ground, and also near these diodes. Okay, so I'll quickly place some. So I place some stitching vias near the grounds. Now one thing I'm noticing here is this 12 volt lines. Okay, so we're connecting these 12 volts to these diodes, but it is being connected only through this 1 millimeter trace. Okay, so what actually we can do is create another copper zone here. Okay, create a whole copper zone, something like this, which can cover all these four diodes. Okay, which will create a larger area for this 12 volts nodes. Okay, so I'm not going to do that now, but as your assignment, just to get the idea, you can try and improve on this motor driver board. Okay, so now what we want to do is we want to actually define the boundary of the board. Okay, we want to actually define how big and what are the dimensions of our board will be. Okay, so for that I'll go to this edge cut layer, and I'll just draw one rectangle covering all the components. Okay, I'll just maybe click here and here. Okay, so I think we are done with our physical design. Now one very important step is to check whether we have done all the connections, whether there are some issues with the board. So we can do that by using design rules checker, DRC. Okay, I'll just click on it and I'll click on run DRC. So what this DRC does, it shows us where we are missing something. If some components are not connected, it is checking the clearance. Let's say we are, for example, let's say we are placing these two traces very close, then it will show an error. So it checks all the design rules, and it gives us a list of errors if something is not right. Okay, so the first error that we see here is something called as clearance violation. Okay, it is showing here. If you click on it, it will actually show that this resistor that we are using, it is violating an error. Okay, so the default clearance is default pad clearance is 0.2 mm. Here it is 0.18 mm. So if let's say the manufacturer is able to only have a clearance of 0.2 mm, but we have a clearance of 0.18 mm, then the manufacturer actually won't be able to make the correct board. Okay, uh, this error we can ignore if the manufacturer is actually able to have a clearance of 0.18, but in this example we'll try to actually fix it. The next error getting is similar to the first one. This is for the second register, so we'll probably change this register footprint. The next error we're getting is via is not connected or only connected to one layer. Okay, so all these vias that we have placed is actually, I think, connected to only the back layer. Okay, so this is an easy fix. So let's just first solve this via issue. It is saying that via is connected to only one layer. Okay, so I think I missed drawing the copper zone layer in the front copper layer. So let's just draw the fill zone of ground in the front layer as well, and I think that will solve our this warnings. Okay, so I'll close it. I'll go to the front layer. I'll click on draw fill zones. I'll go to the edge of the board. I'll assign this copper fill zone to ground, and I'll click on OK, and let me quickly draw it. And I'll press the B key to actually fill this zone with copper. Okay, so I'll press the B key. So it has now filled this zone, this whole front zone with uh, copper, and that zone is assigned ground. Okay, so let's just go back to this DRC and we'll run DRC again. So I think we can see that this via error is now via warning that we got earlier is now solved. Okay, so now let's just quickly solve this clearance violation issue as well. Okay, so I'll close this. I'll actually change this footprint. So I'll select it and I'll change this footprint. Okay, let me quickly change this footprint to a bigger one. I'll type resistor. Okay, I think this looks fine. 1608. I'll click on change and close. Okay, I think I need to reconnect this trace, so I'll delete it and connect it again. I'll delete this one as well and connect it again. I'll do the similar thing for our second register. I'll right click, change footprint, click here, type res, and yeah, we'll change it to this one, metric hand solder 16.8, change and click on close. I think we need to reconnect it. I'll delete this trace and I'll reconnect it. Okay, let me move this register here so we can connect it properly. Connect it here. I'll delete this again. Yeah. Okay, let's just run the DRC again and check. So all our errors are solved. We are getting a very minor warning, that is this. It is saying that uh, the reference field of J4 segment of J6 on cell screen. Okay, so it is saying that this J4 is actually overlapping with this J6. So let's just quickly move this one. I'll hit the M key, select it, hit the M key, just rotate it and place it somewhere here. I think that's fine. Let's run the DRC again. Yeah, so now we're getting zero errors, as you can see here, as well as zero warning. Okay, so I think we have completed this design. We're not going to actually send it to manufacture because this is not a very optimized board, optimized PCB board. So we can actually now view our board that we have just made using this 3D viewer. Okay, so if I click on it, you can actually see this is the board that we have just made. Okay, this is the back layer, this is the front layer. Okay, these are the two capacitor, this is the input power supply pin, these are our diodes, these are the test points through which we can measure the current. You'll see one thing that we have this IC missing here. Okay, so we have this capacitor, but this capacitors, these diodes, these connectors, but this IC is missing. This is because this 3D file, the 3D file is missing. Okay, so let's just also quickly see how we can import this 3D file as well. So what I'm going to do is just type L298 and IC 3D model. Okay, so this is for the whole model. We don't need that. We need this IC. Okay, so I'll go to this SnapMagic website. I'll click on it, and this is the 3D model. Okay, I'll click on download 3D model. If you're not signed into SnapMagic, you need to quickly sign in. I'll just pause my video and quickly sign in. So after signing in, you can just click on download 3D model, and you can choose this step format and click on download. So after you have downloaded this file, we'll go back to our PCB editor. I'll select this L298 IC. Okay, I'll right click, I'll go to properties, and I'll go to 3D model. Okay, and I'll click here to add one, select the folder. Okay, and here is the 3D model. I'll open it. See, so this is the 3D model. So now you can rotate it using this X, Y, and Z values. I'll rotate it. So I need to uh, adjust it properly using this offset. So I'll bring it back and a little bit upside so that I can arrange these pins. This looks fine. I think this looks fine. We can maybe bring it down a bit. Yeah, this looks fine. So I'll hit on OK, and we have successfully imported this 3D model. So if I click here, now this 298 IC appears. Right, you can see here. Similarly, you can also import this voltage regulator. You can just type on Google L7805 3D model for KiCad, and you will get the model, and you can import it in a similar fashion. Okay, I'm not going to do that because I don't want to drag this session any longer. So I hope I was able to cover some very fundamental concepts involved in PCB design. We have taken a very simple project, this L298 motor driver. It is very commonly used, so I picked this project for now as an initial start, just to give you the idea how to connect components, how to read data sheet, what are footprints, how to use capacitors, how to connect different components, what is design rule check, what are vias, what are copper fill zones, how do we choose the trace width. So no matter what projects you design, if your fundamentals are very clear, you'll be able to design and optimize many new projects. So this is it for this session, and from the next session onwards, we're actually going to build some design or build some product which have some practical problem statement. Okay, thank you for watching.